Hello guys, in the last class we had discussed about alkanes, alkenes and alkynes and their naming and different variations in the branches what we can have in these open chain structures. Now we are going to talk about cycloalkanes and cycloalkenes. So basically now we are talking about the closed chain naming. Okay, in today's class we'll be a little faster because we know the basics of naming now. We know how to mark a chain, how to number a chain, how to name a chain, what is word root, what is suffix, what is prefix. At least we are aware of these terms now, and we are much more familiar than when we started the nomenclature. So my speed will be a little faster. Try to match with yours, and just in case if you don't understand something, ask me in the downs class. Okay, so we'll be starting with the namings of cycloalkane. Now cycloalkanes are the closed chain alkanes where there are no two ends. So basically cyclic chain is the one where any carbon can be marked as carbon 1. And now there are also rules how to decide which carbon is carbon 1, which carbon is carbon 2, if there are any substituent groups present, or if there are any branches present or any groups present on the cyclic chain. But if there is nothing present on the cyclic chain, in that case any carbon can be taken as carbon 1. Okay, how do we name it? So we have prefix for cyclic structures, and that prefix is cyclo. So we mark cyclo as a prefix. This is called as primary prefix, and the name will be cyclo plus word root plus suffix. Now here again, your cyclo represents that the chain is cyclic, word root represents the number of carbons present in the cyclic chain, and suffix represent what kind of bonding is there. So cyclic chain can be a saturated chain and can be an unsaturated chain also. If it is saturated, then it will be ane. If it is unsaturated, depending upon it has double bond or triple bond, we will have ene and ion. So basic rules of naming remain same. Only thing is we have to use cyclo as a term to represent that this is not an open chain but a cyclic chain. So let's quickly check. Now here I have a structure which is made up of 3 carbons. I hope you remember we had done bond line structures, and at that time I told you that we won't represent the bond line structures with carbon or hydrogen. It will be just line, and the endpoints of that line will represent carbon, and we assume that the hydrogens are completely filled depending upon the valency of the carbon. So valency of the carbon is fulfilled by hydrogens. Okay, so if I have this structure, that means I'm talking about CH2, single bond CH2 and single bond CH2. If you don't know how to write why it is CH2 and how did we suddenly got CH2, you can just simply mark carbon, carbon and carbon, and then remaining valencies which are unfulfilled can be filled by hydrogen. So this is the structure what we are talking about. So this structure is made up of 3 carbons. Okay, so word root is going to be prop. All are single bonded, so ane and cyclo to represent that it is a cyclic chain. So the name way is going to be cyclopropane. Cyclo is prefix and propane is the name of the chain. Similarly, I have next compound, that is cyclobutane, 4 carbon chain. Okay, all singly bonded, so cyclobutane. Next is 6-membered chain. It's something like this. I'm not filling hydrogens, and I hope you will understand that all the valencies are already fulfilled by hydrogen. So 6 carbon chain, 6-membered carbon chain, and because it is cyclic, we will name it cyclo and hexane. There will be no gap in the name, as we have already discussed this before, that IUPAC naming, in the IUPAC naming we don't have any spaces. Now look at this compound. This is 1 carbon here, 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 and here. So total 10 carbons are there, and this is cyclodecane. So that's how we name a cyclic chain. The whole procedure remains same. Only thing is we have to use prefix. There are definitely certain rules which are associated with cyclic rings, and we will learn them step by step. So these were the names I had shown you where we didn't had any group present on a cyclic ring. The cyclic ring was simple, normal cyclic ring without any branches, without any substituent. Substituent means anything it can be. It can be a carbon chain, it can be a functional group, it can be anything. Okay, so there are no substituents present on these cyclic rings, what we have discussed just now. And now we'll be talking about the cyclic chains where there are some substituent groups present. If there is a substituent group present, how to name the cyclic chains? So let's go by the first rule. We can have, see, as in the normal carbon chain, we can have a carbon chain like this. Let me just draw it. So I can have a chain like this where I have carbon, 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 and assume all the hydrogens are already filled, okay? And then I have a carbon over here. So what we do is we take the longest possible chain, and then we take the one which is out of the chain, we take it as a branch or substituent and name it in the prefix. Right? So exactly same way, you can have branches on the cyclic ring also, and those branches can be open chain, can be closed chain, can be doubly bonded chain, can have some functional groups present on it. Now, depending upon which part of the molecule you have to take as the principal chain, or we can say primary chain, or which part we have to take as a branch, that we have to decide on the various factors. Okay, so assume I have a cyclic structure. I have a cyclic structure which has a branch on it. Okay, so for example, I have written over here, this is a 3-membered cyclic ring and one carbon chain on it. So if I write it in the simple form, basically if I write it in the terms of carbons, how will it be? It will be like carbon, 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 and then there is a carbon over here. That is as a branch. Okay, now whether I have to take that as a branch or I have to take a cyclic part as a branch, that we have to decide. So we cannot say which part is branch and which part is a principal chain. That will be decided on various factors and various rules. So let's see how to choose the principal chain in case of the cyclic structures, and which part will be branch, which part will be principal chain, how we will decide on it, how we will write the names. The first rule is, when ring contains more or equal number of carbon atoms, then the alkyl group attached to it is named as derivative of cycloalkane. The cyclic group, the alkyl group, is treated as substituent. See, I will explain you this in the simple language. What they're trying to say is, if you have a cyclic chain and if you have a branch on it, just we don't call it branch, let's say it has an open chain attached to it, we have to check which of the two species have the more number of carbons. Is it the cyclic ring which has more number of carbons, or it is the open chain structure which has the more number of carbons? Whichever has the more number of carbons will be acting as the principal chain, and other part will be acting as a branch. Okay, let's see with the example, you will be able to understand more. So in this case, if you see, my cyclic chain has 3 carbons, whereas the open chain has only 1 carbon. So open chain will be acting as a branch, whereas my cyclic ring will be acting as a principal chain or the primary chain or the parent chain, whatever you want to call it. Okay, so this is my parent chain, and this carbon or CH3 will be acting as a branch. So how will we name the principal chain? We already have learned that this is named as cyclopropane. Why cyclopropane? Cyclo because it is cyclic, and propane because the main chain contains 3 carbons, all singly bonded. And we also have learned this, that we have to name the branches in the beginning of the name. So basically, your cyclo is the primary prefix and the branch name is the secondary prefix. So name will be this way. You will be writing secondary prefix plus primary prefix. This 1 degree is nothing else but primary prefix plus principal chain name. That's how we name the molecule. Okay, the secondary prefix is the branch name or the substituent chain name, and primary prefix represents what kind of chain we have. Is it an open chain or the closed chain? For open chains, we don't have any primary prefix. For the cyclic chains, we have the prefix as cyclo. Okay, so this is the branch. What we have here is CH3. We all know the name of the CH3 is methyl. Now comes to the position, how to position these branches. As I have mentioned this earlier also, that in the cyclic chain we can choose any carbon as carbon 1. So always we have learned that we will try to give our branches the lowest position possible. So why not mark this as carbon 1, carbon 2 and carbon 3. So the carbon on which CH3 is present, let's assume that is carbon 1. So we will write it as methyl cyclopropane, or you can also write it as 1-methyl cyclopropane. I have written space. I mean, this is my mistake. I just wanted to be a little more neater. But when you will write it in the actual exam, you will not leave any space between the names. So it is 1-methyl cyclopropane. That's how exactly you will be writing without any space. Okay, now look at the next compound. In next compound, again, my ring has how many carbons in it? 3. And my open chain has how many carbons? 2. So open chain, 2 carbons. So which one is lengthier? Which one is bigger chain? The cyclic one is the bigger chain. So cyclic one will be acting as the parent chain or the principal chain, hence the name will be cyclopropane. And because my branch is made up of two carbons all single bonded, the name will be ethyl. We can again assume that it is present on the first carbon, and hence we can write ethyl cyclopropane, or we can write 1-ethyl cyclopropane. Similarly, look at the next compound. In next compound, what we have, ring is made up of three carbons, and the open chain is also made up of three carbons. Now comes the question, which one to choose when both have the same size? In this case, we will be choosing whenever there are the comparable sizes or the same size for the open chain as well as the closed chain. We will always choose the closed chain as the main chain or the principal chain. So irrespective of both have same sizes, your cyclic chain will be acting as the primary chain, principal chain, or the parent chain, whereas the open chain will be acting as a branch. So now we know that our branch has three carbons, one here, and one here, and all the three are singly bonded. This branch name is going to be propyl. And my cyclic chain name is cyclopropane. And again, I can mark its position as position 1, 2, and 3 like this. So 1-propyl cyclopropane. That's how we'll be naming it. Now comes to the next part or the next example. If now you will see in this question, what we have is ring is of 3 carbons, whereas my open chain is of 4 carbons. Which one is lengthier? The open chain is lengthier. So now the case is reverse. What we are doing now, in this case, my open chain is acting as the principal chain, whereas my cyclic chain is acting as a branch. So how will we name it? We know this open chain is made up of 4 carbons, all singly bonded. So 4-membered carbon chain, all single bonds, is called as butane. Now how to name this branch, cyclic chain as a branch? How do we name it? Cyclopropane instead of propane, it will be propyl. Why propyl? Because it is a branch. It is a branch, and that's why we have already learned what are alkyl groups. Similarly, we have cycloalkyl groups. Cycloalkyl groups are nothing else but when you remove one hydrogen from the cycloalkane chain, then the compounds are called as cycloalkyl, and these are branches. So we call it as cyclopropyl. Now again, how will we number the principal chain? The point of attachment here is what matters. I can start my numbering from here, from left to right, and I can start my numbering from right to left. Either way, I mean right to left and left to right, but the smallest number we have to give to our branch, and hence I'll start numbering from here 1, 2, 3, and 4, and automatically my cyclopropyl will get the position 1. So 1-cyclopropyl butane is the name. You can just simply ignore writing 1. I hope you would have understood it. Let's go to the next rule. So let's talk about the next rule now. Next rule says the numbering of carbon atom in the ring is done in such a way that the substituent which comes first in the alphabetical order is given the lowest possible number. It does not violate the lowest set of Loken's rule. So basically what we are trying to say is, if I have a cyclic ring and if I have multiple open chain structures present over there, then how to decide the numbering? We will always try to give the lowest possible number to one of the substituent which is alphabetically first in the order. For example, if I talk about this particular compound, in this compound we have a cyclic ring and I have two branches over here. Why I'm calling them branches? Because it is clearly visible that the cyclic ring is made up of 6 carbons and the branches have only 1 carbon and 2 carbons. So these are going to act as branches. My main chain name will be cyclohexane. There is no doubt about it. Now we have to find out the positions of these branches. This branch is methyl and this branch is ethyl. We have to find out the positions for them. What is the rule to find out the positions? Whichever comes first in the alphabetical order should get the lower number. Okay. But make sure that you do not violate the lowest sum rule. That means the sum of the positions should not come greater or higher. What do I mean? Let me just explain you. There are two ways of numbering this chain. CH2, CH3, and this is CH3. Okay, now I can number it in such a way that I start numbering from here 1, 2, and 3. In this way, This ethyl should get the lowest position, by the way. Why? Because it is alphabetically first. Okay. And other way is I could also number it 1, 2, 3, 4 and 5. So in the first case, my branch is getting position 1 and position 3. So total sum is coming out as 4. If I use the another way of numbering, which I have done just now, the second way of numbering, in that case, my one branch is getting position 1, the one which is alphabetically low, that particular branch is getting position 1, whereas the other branch is getting position 5. It is violating the sum rule. So basically, even though my alphabetically ordered, through my alphabetically ordered, whatever the branch is getting priority, that is getting position 1, but the other branch is getting some far away position which is violating the sum rule. Okay, so out of these two positions, 1 plus 3 or 1 plus 5, we will be following 1 plus 3. So my one branch will get position 1 and another branch will get position 3. So my methyl, so I'll number it this way, 1, 2 and 3. My ethyl will get position 1, my methyl will get position 3. And now I will arrange these names in the alphabetical order while naming it in the prefix. So I will be writing as 1 ethyl, 3 methyl, cyclohexane. Simple. Look at another example. Another example I have again 6-membered cyclic ring. Clearly visible that this is the bigger chain. So the cyclic chain name will be cyclohexane. I have 3 branches, 1 methyl and 2 methyls and 1 ethyl. Now I have to figure out the positioning of the carbon chain. Positioning can be done in the multiple ways, but we have to follow it in certain way that the alphabetically first whichever branches should get the position 1, as well as we have to follow the lower sum rule. That means all the positions of all the substituents should get a lower sum. That is also we have to follow. There are multiple ways. Let me just figure out what all different ways are there. I can show you. One is I start numbering from here 1, 2, 3, 4, 5. So by this way I'm getting position 1 for C2H5, which we want. Then I'm getting position 2 and then I'm getting position 5. This is one way. Okay, let me just try out the other way also. So other way is I can number it as 1, 2, 3, 4 and 5. In this way what I'm getting is 1, 3, 5. Okay. The other way of numbering is I mark it 1, 2, 3, 4 and 5. So I got 3 locants, 1, 3, 5. Okay. Now let's see if there is any other way. See, if I talk about the first set of positions, then I get the sum as 8. Correct? If I talk about this set of locants, then the position is 9. I mean, the sum comes 9. So obviously this is completely ruled out. Let's figure out, is there any other way also where we can get a lower sum? So basically what we have to do is, it's not like always we have to try to give position 1 to the alphabetically order, the one which is alphabetically first in the order. We don't have to always give it position 1. We have to try to give it lowest possible position along with the lowest sum rule. That means just in case if I do a little tweak here and there, and the total sum of the positions come even lesser than 8, I will follow that. Okay, so lowest sum is the higher priority, and we have to also make sure that our alphabetically order first substituent should get the lowest possible position, whatever it can get. Let me just explain you again with the help of this example itself. So we have got 2 positions now. We have got 1, 2, 5. We have got 1, 3, 5, and I have ignored that because the sum is coming 9. And I will try the third way, whether it is possible to give it any other position or any other position to all the 3 substituents so that we get a lower sum. Let's figure it out. So let me just rub these positions. Let me try numbering it from here. 1, 2, 3 and 4. If I number it this way, what positions I'm getting position 1, I'm getting position 2 and I'm getting position 3. So overall sum is coming 7. But what is the concern over here? The concern is my ethyl, which was alphabetically first, is not getting position 1 now, is getting position 2. Okay, but it's okay. But it's completely okay. Why it is completely okay? Because the sum is coming 7. Let me just take one more example. Okay. Or let's talk about the previous example itself. So we had two substituents over here, methyl and ethyl. Where it was possible to give ethyl the position 1, we could have given it to methyl also, but we didn't. Why? Because alphabetically ethyl gets preference and hence the position is 1. But in the other case, in no matter whichever way you do, you have to give methyl as position 1 because this is giving you the lower sum, and lower sum has a higher priority. And then once you get the lower sum, then you figure out, I mean, which way or which is the lowest possible position you can give to your alphabetically first functional group or the substituent chain. Okay, so neither I'll follow the positioning 1 2 5, nor I'll be following position 1 3 5. Instead, I'll be following the position 1 2 and 4. I will be marking methyl 1, then ethyl 2, then 3, and then 4. Again, as I mentioned, the reason is we have to follow the lowest sum rule first. We have to try to ensure that the sum should be lesser, and then whatever in that, the lowest position possible, my alphabetically first substituent should get. So the name is going to be 2-ethyl 1,4 dimethyl cyclohexane. That is why if you see in the rule, I have clearly mentioned that we have to give the lowest possible position to the one which comes first in the alphabetical order, but it should not, or it does, and make sure it does not violate the lowest set of Loken's rule. Okay, now similar example is there, is the third example. Now here if you see, I can mark position 1 2 and 3. If I start numbering from ethyl, in that case my ethyl will get position 1, but my methyls will get position 3. So the sum will be 1 plus 3 plus 3. Whereas if I start numbering from methyl and I mark ethyl 3, in that case the positioning will be 3 plus 1 plus 1. So this is giving me the lower sum. So I will prefer this one. Okay. So 3-ethyl 1,1 dimethyl cyclohexane. What could be the other way? Other way could be I could have started marking from here 1, 2, 3, 4 and 5. In this case, if I go by this numbering, the numbers which I'm getting is 1 plus 1 plus 5. This is not what we are following. Here is the thing where we have to use this rule, that my alphabetically first substituent should get the lowest position possible in the lowest sum of locants or lowest set of locants. So we had option of giving it 5 and we had an option to give it 3. I mean, basically ethyl could be on the 5th position or ethyl could be on the 3rd position. But did I give it that way? No. We had used 3 plus 1 plus 1 and the sum come out to be 5. This is the lowest sum possible. So the name is 3-ethyl 1,1 dimethyl cyclohexane. Okay. Try out these questions. These are important, and more questions of this type you'll do and more clarity you will get. Here again, let me just emphasize on one thing. Alphabetical order of substituent is important, but lowest sum is more important. So lowest, your substituent should get the lowest sum first. Their positions sum should be lower, and then you will find out what lowest possible position you can give to your alphabetically first substituent. Okay. Similarly, look at this next question. In this next question, we have three substituents on our cyclic ring. One is iodo, another is bromo, and third is chloro. Now we have to figure out how to number it. But before that, we have to figure out which substituent group is getting the higher priority in terms of alphabetical order. So we have name for iodo as iodine as iodo, bromine as bromo, and chlorine as chloro. So all of us know that the bromo is alphabetically first. Okay, so let's figure out different ways of numbering it. Let me draw the multiple chains so that you can compare all of them together, because I keep rubbing stuff. And this is IBRCL, IBRCL, and again IBR and CL. Okay, I may make more chains depending upon do we need it or not. So the one way is I give lowest possible position to my bromine, that is one position, and I might mark it as 1 2 3 4 5 and 6. In this case I will get some as, or I will get the positions as 1 plus 2 and plus 6. Okay, if I would have gone other way around, then also I would have got the same 1 2 3 4 5, and 6. Again, the sum would have been same, so I'm not taking that set of alkanes, or I'm not marking it again. No matter you go clockwise or you go anti-clockwise, if you're giving bromine as the position 1, basically the numbering is going to remain same. Okay. Other ways I can start my numbering from iodine. So it is 1, it's 1, 2, 3, 4, 5, and 6. So positions, what you're getting is 1 plus 2 and plus 3. And if I start my numbering from chlorine, I'll get position 1, 2, 3, 4, 5, and 6. Again, 1 plus 2 plus 3. So giving the lowest number to bromine is giving you 1 plus 2 plus 6. Basically, obviously the highest sum. Though your bromine is alphabetically first and getting the lowest number, but the sum is not lowest, hence we will not consider it. Okay, now we have two options. We can start numbering from iodine, go till chlorine, or we can start numbering from chlorine and go to iodine. Now here, bromine in either case will get the position 2, but that is the lowest possible position your bromine can get along with the lowest sum rule. So what we will do over here now, bromine is anyways getting the second position. So let's try to give the lowest possible position out of iodine and bromine, whichever comes alphabetically first. Let's try to give it the lowest position. So out of chlorine and iodine, chloro comes first in the alphabetical order, and hence we will start numbering from chlorine, and it will be 1 plus 2 plus 3, this way of numbering. Okay, so we will ignore this, we will ignore this, and we'll follow this. In this case, bromine is definitely not getting the first position, but whatever the best possible position it can get is in the lowest number, it is getting that. So the name will be 2-bromo, 1-chloro, 3-iodo, cyclohexane. Now exactly same situation we are facing in the next question also. So we have now 4 substituents over here: iodine, bromine, chlorine, and fluorine. When you talk about the alphabetical order, bromine should get the first position or the lowest position. But if I'll do so, my positions will be bad, or you can say will give you the highest number. If I start numbering from bromine, it will be, let's say, 1, 2, 3, 4, 5, and 6. If I'll do this way of numbering, in that case, I will have sum as 1 plus 2 plus 3 plus 6, whereas okay, so this is one sum, and the other way is I can start numbering not from the middle but from the starting, because here I'll get the consecutive number. No matter I go from clockwise or anti-clockwise, I'll get 1, 2, 3, 4, and that will definitely give me the lower sum. I have to figure out fluorine comes first in the alphabetical order or iodo. So all of us know F comes first in the alphabetical order. So I will start numbering from fluorine. So position will be 1, 2, 3, and 4. And this gives me the lower sum. Along with that, my bromine gets a position 3. So we cannot give it a better position. The best possible position I can give to my bromine is 3, along with the lowest possible rule. So here I had given preference to fluorine. Bromine could have got second position if I would have started numbering from iodine, but in that case iodine is higher in the alphabetical order as compared to fluorine, so we can't do so. So that's why I've started numbering from fluorine. The sum is anyways gonna remain same, and my bromine is going to get the third position. So the name of the compound is going to be 3-bromo, 2-chloro, 1-fluoro, and 4-iodo cyclohexane. I hope you have understood what we are giving preference as, what is our more priority thing and what is the lesser priority thing. You have to follow it diligently, you have to understand it, and if you're not getting it, try solving multiple different questions of the similar type so that it gets in your mind, you understand the rule properly. Just mugging up the rule will not help you because the rules keep changing depending upon chain to chain. Okay. Let's talk about the next rule. If the functional group is present in the cyclic compounds, then the main chain is taken in which the functional group is present. If the functional group is present on both the side chains as well as the ring, then the main chain will be taken which has the maximum number of carbon atoms. So what exactly we are saying over here? I have a cyclic chain and I have an open chain. Let's say this is my open chain. Now there is something which we call as functional group. Functional group like chlorine, bromine, iodine, alcohol, or nitro, or carboxylic acid, aldehyde, ketones, anything. Though we have not spoken about these functional groups yet, but still we can understand the rule a bit, and then we will follow the same rule when we will learn functional groups. Okay, so if we have a functional group present in the molecule, now where the functional group is present will decide which part of the chain is going to be the principal chain or the parent chain. If the functional group is present on the if the Fg is nothing else but the functional group. So if the functional group is present on the open chain, then irrespective of the size of the open chain, my open chain will act as the principal chain or the parent chain. Why? Because it has functional group. It has additional one important thing, that is functional group. It can be a functional group, it can be a double bond, it can be a triple bond, it can be chlorine, bromine, iodine, anything. Whatever is present on the open chain, if it is different, it is an unsaturation or it is a functional group. If it is in the open chain, then the open chain will be taken as the primary chain. If it is in the cyclic chain, then the cyclic chain will be taken as the primary chain. If let's say the same thing is present in both both the areas, in that case there are further some rules to decide on it. Okay, then we will start from the beginning, which has the bigger chain, and then we will start taking that as a principal chain. If the sizes are also same, then also there is a rule. So we will come to it slowly. For now, you have to understand wherever the unsaturation or the functional group is present, that will be taken as the main chain or the principal chain or the parent chain, and the other part will be taken as a branch, and you have to name it accordingly. So let's talk about the examples now. Here I have taken two examples. You can see it very clearly. I have a cyclic chain. Cyclic chain is made up of 3 carbons, and I have a open chain also, that is also made up of 3 carbons. So basically number of carbons in the open chain as well as in the cyclic chain are exactly same. And we can see that there is, in the first example, we have a chlorine present on the open chain. So I mentioned just now that if a functional group, wherever the functional group is present, will be taken as the main chain or the principal chain, and the other part will be taken as a branch. So which will be branch over here? Branch is going to be our cyclic chain. This is my branch, or substituent chain, or side chain, whatever you want to call it, and this will be called as cyclopropyl. Whereas this chain will be acting as the principal chain. Now how to name the principal chain? We already know it. The name of the principal chain is propane. But in the propane, what all we have as a branches, we have chlorine as a branch or the substituent, and we have a cyclopropyl as a substituent. Numbering will be done in such a way that the sum should be lowest and branches should get the lower number. So I could have started from here 1, 2 and 3, or I can start from here 1, 2 and 3. So I'll follow this way of numbering. Why? Because it will give my cyclopropyl branches position 1 and chlorine as position 2, and sum is the lower over here. Okay, so the name will be 2-chloro 1-cyclopropyl. Why it is 2-chloro? Why not 1 cyclo before 2-chloro? Because we ignore the term cyclo when we are comparing the alphabetical order. So here we are comparing C and P, and C comes first in the alphabetical order. That's why it is 2-chloro 1-cyclopropyl propane. So now let's talk about the second example. So in the second example, what we have, my carbon chain here is made up of 4 carbons, and the cyclic chain, so open chain is of 4 carbons, and the cyclic chain is made up of 3 carbons. But what is important over here, that my cyclic chain has chlorine, that is a functional group which is present on the cyclic chain. And just now we have discussed any chain, no matter it is cyclic or open, if it has a functional group, it is going to be the main chain irrespective of its length. So irrespective of its length, the cyclic chain is going to be the main chain. So the name of this cyclic chain is going to be cyclopropane. Okay, so my principal chain is cyclopropane. What all branches I have? I have butyl as a branch because it is made up of 4 carbons, and I have chloro as a branch. Now how to number? Again, we will look out for the alphabetical order in this case. Butyl comes first in the alphabetical order, so I'll number from here 1, 2 and 3, because irrespective of you start numbering from chlorine to butyl or butyl to chlorine, the sum will remain same. So I will try to give the lowest possible position to the substituent having better preference or precedence in the alphabetical order. So butyl will get position 1, chlorine will get position 2, and the name will become 1-butyl 2-chlorocyclopropane. Is this clear to everyone? I hope it should be, and we will be doing more questions on it once we will understand more functional groups. But for now, because you knew only halogens, so I had just given you some examples using halogens. Later on, we will be talking about other functional groups attached on the cyclic rings or on the open chains and so on. Okay, so now let's talk about the next rule in the ring system. Now there is a possibility that you may have multiple rings present and all those rings are attached to each other through an open chain. Okay, for example, I may have a cyclic chain and then I have CH2, CH2, CH2 and then one more cyclic chain. So it is a multi-ring system which is connected with each other through an open chain. So if I get any such system, how exactly we have to name it? What is the rule behind it? So rule is irrespective of what is the length of your chain, that is open chain I'm talking about, or what is the length of your cyclic chain. What is going to be your principal chain? Always and always and always and always, in such cases, open chain irrespective of its length is going to be the parent chain, and your cyclic rings, no matter they are larger in number, they have more number of carbon atoms in them as compared to the open chain, irrespective of whatsoever, these chains are going to act as the branches. Okay, so here we had all both had the same numbers. Basically the cyclic ring also had 3 carbons and the open chain also have 3 carbons. So here there is no such confusion and we can follow this rule, but I could have this in a shorter way like this, which I have given over here, that the open chain is made up of only 1 carbon, whereas your cyclic ring has 3 carbons. Now irrespective of either case, your open chain will act as a main chain and your cyclic chains will act as the branches. Okay, so what will be the name in this case? Now we know this is my principal carbon chain. Principal carbon chain has 3 carbons over here, so it is propane. And now I have 2 cyclic chains as branches, so it will be cyclopropyl, not cyclopropyl. Instead, it will be dicyclopropyl. The position will be 1, 2, and 3. So 1, comma 3 dicyclopropyl. My bad, I'm just running out of space. So 1, comma 3 dicyclopropyl propane. That's how the naming will be. Look at this example. So this is also 1 carbon over here and the main chain is methane and we'll be writing it's tricyclopropyl. Why I have not mentioned any positions over here? Because there is no other possible position. There is only 1 carbon over here. Okay, so tricyclopropyl methane. Similarly here, if you see, we have 2 membered carbon chain as an open chain and 6 membered cyclic rings. So the name is 1, 1, 2, 2, 1 and 2, 1, 1, 2, 2 tetracyclohexyl ethane. So in all the cases, you can see that the center chain or open chain is the smaller chain and the cyclic rings are the bigger ones, but still we are taking the open chain as the main chain or the principal chain. Now let's talk about the last rule of cycloalkanes, and then we will go to cycloalkenes and alkynes and we will learn few more things about them and how to name them. Last rule is if my cyclic ring is directly connected to benzene ring. What is benzene? C6H6. I have shown you the structure of benzene earlier also. This is a 6-membered cyclic chain with the alternate double bonds. This can also be represented as the circle in the center. Why it is represented with the circle in the center? Because the double bonds keep switching their positions with respect to each other, and but they still remain in the alternate positions always. Okay, so this can be a benzene structure or the benzene structure can be this. So these are interconvertible. So basically the double bonds keep rotating inside the ring and that is why we put a circle inside. Okay, so if the benzene ring is attached to your cyclic ring, in that case, no matter what, your benzene will be acting as the main chain and your cyclic chain will be acting as a branch. So we have written it as benzene cyclohexyl or cyclohexyl benzene. Cyclohexyl is the branch and benzene is the main chain. Now here the chain could have been a bigger chain also, but still it would act as a branch. If it would be a 7-membered ring, then the name would have been cycloheptyl benzene. If it would be a 5-membered ring, it would be cyclopentyl benzene, but benzene will be acting as the main chain. Why? Again, just use the common sense that we have double bonds in this chain. So anything which have double bonds, unsaturation, functional groups, that will be acting as the principal chain or the primary chain. And that's why benzene is the parent chain over here and the cyclic ring is acting as a branch. Okay, so now let's talk about naming of cycloalkenes. We have already understood how to name the cycloalkanes, what are all different rules which are associated with cycloalkanes. Now it is the turn of cycloalkenes. So what exactly are cycloalkenes? Again, the cyclic structures which carry at least one carbon double bond carbon are called as cycloalkenes. Okay, so that means the presence of one carbon double bond carbon is must. It can have multiple double bonds, but at least one carbon double bond carbon must be there. Now, apart from that, there are few important things which you have to keep in mind while naming and numbering the carbon chain or the cyclic chain when it is an alkene. That is, when you have cycloalkenes, it will have a carbon double bond carbon. Okay, and the carbon double bond carbon will always get the position 1 and 2. That means the positions of carbon double bond carbon are going to be continuous, and one carbon will get position 1 and another carbon will get position 2. So it is specific to the case where you have only one carbon double bond carbon. So let's say if there are multiple double bonds, so in that case your numbering will start from carbon double bond carbon, and then the other double bonds will also get their positions respectively. Always remember, if the first carbon you have taken as carbon double bond carbon, the other carbon will also be carbon double bond carbon. So it will never happen this way. Let's say you have a chain like this. Okay, assume this is the chain and it has a pi bond over here. So as I mentioned that your carbon carrying double bond will always get position 1 and 2, continuous in nature. It will not happen that I'll mark this carbon as 1 and then this is 2 and this is 3. This is the wrong way of numbering. This will always be one number for this. I'm sorry, let me write with a different color. So one number for this and two number for this. So basically, wherever the double bond exists, those two carbons will get position 1 and 2. Okay, so that's very important. This point is very important. We will be discussing this point later on and we'll be applying it everywhere whenever we'll talk about the naming and numbering of the cycloalkenes. Okay, so let's quickly go through the rules of cycloalkenes naming. The rules would be very similar to what we have learned in cycloalkanes. There are few changes, there are few important things, there are few add-ons in the rules what we have to understand so that we can use them and directly start solving the question. Again, my speed is going to be faster, faster and faster. Earlier when we started nomenclature, the speed was quite slow, and now because I feel that you are much more familiar with the rules now and the things are becoming little obvious for you guys, so I'll increase the speed here. I have listed down few rules. I'll just quickly iterate the rules here and then we'll tell you how to apply it by using different examples. So first rule what we have got here is, if the ring has unsaturation and the side chain is saturated, then ring is selected as a parent chain. So let me just give you an example for it. Very quick example, though we will do all these rules in detail with a different example. So let's say I have this as a chain and I have a side chain. Side chain is not carrying anything, any double bond, any triple bond, whereas my ring is carrying a double bond or unsaturation. In that case, irrespective of the length, my ring is going to be the parent chain and my branch is going to be this open chain. So this chain has 4 carbons, 1 here, 2 here, 3 here and 4 here. Whereas in my cyclic chain, I have a double bond in the center. So this has the unsaturation. The cyclic ring has an unsaturation. So irrespective of its length, this is going to be my principal chain, parent chain or primary chain, whatever you want to call it. Now, if it would be other way around, let's say if my side chain would have, let's say this is my cyclic chain. Let's not take this one. Let's take a little bigger one. Okay, because I'll be actually using two rules over here. We'll be simultaneously teaching you two rules. So here I have taken this ring, which is made up of 4 carbons, and I have an open chain with just 2 carbons and double bond. Again, in this case, as I mentioned, number of carbons don't matter, but double bond does. Okay, so because this particular chain has the pi bond, this will be acting as the principal chain or the parent chain, whereas my ring will be acting as the branch. Okay, so wherever the double bond is, that particular ring or chain will be acting as the parent chain, and rest of the part will be acting as a branch, irrespective of length. So we will not be considering length as a parameter to judge the parent chain over here. So third rule is, if both have unsaturation, then the chain with the maximum unsaturation is selected as a parent chain. That means, now let's say double bond is there in the cyclic chain also and in the open chain also. Then whichever will have the maximum number of double bonds, that will be selected as a main chain. For example, if I say I have one double bond here, one double bond here, and then comes this. So now here this chain, the cyclic chain, also has unsaturation, and the open chain also has unsaturation. But the one which has maximum number of double bonds or unsaturation will be taken as the parent chain. So this will be acting as the primary chain, and this is open chain, will be acting as the side chain. Okay. Now, let's say if both have the same number of double bonds, so there is no difference in the double bonds. Let's say I have, again, let me take the same example, but with one double bond. Mm, So let's say this is the chain. Now double bond exists in the side chain also, and double bond exists in the cyclic chain also. Then we will look at the size of the chain. Okay, because double bond exists in both. Now there must be some parameter to judge which one will be taken as the primary chain, which one will be taken, not primary chain, basically principal chain, and which one will be taken as a side chain. So here, if you talk about the cyclic chain, it is made up of 4 carbons, whereas if you talk about the open chain, it is made up of 3 carbons. So the length of cyclic chain is bigger than the length of side chain, and hence this will be taken as the principal carbon chain or the parent chain, and this will be acting as the side chain. Now, the last rule is, if unsaturation and the number of carbon atoms both are same. Now, let me take this example. This is the example I have taken. So this is my I have a ring with the 3 carbons and 1 double bond, and I have an open chain with 3 carbons again with 1 double bond. So now here comes the thing where you have double bond in the open chain also, you have a double bond in the your cyclic chain also, and the number of carbons are also same. So then how will you decide? In that case, you will always prefer cyclic chain over open chain, and hence your cyclic chain will be taken as the parent chain. Okay, so till the time length differs, you will give priority to length. When the length is also same, number of double bonds are also same, then you will give the importance to the shape, or you can say importance to the type of chain. So if it is cyclic, then it will be parent chain. If it is non-cyclic, then it will be side chain. Okay, so here are some rules. Now let's use these rules in detail on different examples, what we'll be doing in the next slide. So now you have to keep all these rules in mind, note them at one place, and whenever you see a question, try to apply these rules and solve the question, give them the names, because basic rules of naming are not changing. Only there are few add-ons which are varying or which are adding because of the change in the structure of the molecule. Okay, so now let's quickly discuss some examples for the same. So let's talk about the first example. First example, what we have is a cyclo structure with the 3 carbons and a double bond. So I have already told you, for a cyclic compound or the closed chain compound, we use the prefix as cyclo. Then we count the number of carbons, which tells you the word root, and then we check what kind of chain it is, doubly bonded, triply bonded, singly bonded. Accordingly, we put the suffix. So here your main chain name will be propene, and cyclo will represent what? So cyclo will represent whether this chain is an open chain or the closed chain. So closed chain, we will be using cyclo as a primary prefix. Okay, so the name is cyclopropene. I hope there is no doubt about it. As I mentioned earlier also, that carbon, double bond carbon will always get position 1 and 2. So automatically the position here for the double bond is 1, hence we have not mentioned explicitly over here. Okay, now let's talk about the next example. Next example, we have a 3-membered ring, cyclic ring, and 1 open chain, which is 1 carbon. So I can write this 1 carbon as CH3 also. Okay, I have an open chain with CH3. I have a closed chain made up of 3 carbons with a double bond. Now I have to name this structure. Before naming, what we will do, we will start numbering. So here numbering preference will be given to the double bond rather than the branch. Which one will be acting as a branch? The open chain will be acting as a branch. Why? Because the double bond is present in the cyclic chain. So this is my branch. This cyclic chain is my parent chain, and I'll number the carbons like this. So I have two options. I can put 1 here and 2 here. Okay, because we have to give carbon double bond carbon is position 1 and 2. So either I can put position 1 here and 2 here, or the other way is I can put position 1 here and 2 here. Now which one is preferable? The one which will give you the lower number to the double bond as well as the lower number to the branch also. So if you see, my double bond is anyways getting the position 1, no matter you number from here or you number from here, the double bond is getting position 1. But if I number from here this way, then the branch will also get position 1, which is most preferable. So we will number the carbon where the branch is present and the double bond, both the things are present. I'll position it 1 and the other is 2. The previous numbering we will not take, and the name of the compound will be 1-methyl cyclopropene. Similarly, now look at this question. So here again what I have is, we have a branch that is CH3 as an open chain structure, and then I have a cyclic chain made up of 3 carbons with a double bond. So hence automatically my cyclic chain is going to be the parent chain. Now comes the numbering. If there are two ways again to number the cyclic chain. One way is I can number 1 here, 2 here and 3 here. This is one way. And the other way is I can number it as 1 here, 2 here and 3 here. But as I mentioned earlier, when we started the naming of the cycloalkenes, I told you always and always you have to give the continuous number 1 and 2 to the carbon double bond carbon. Hence, this pink way of numbering, this way of numbering is wrong, because here I'm giving first position to the carbon double bond carbon, then third position to then the second position to my CH3, and third position to the another carbon carrying a double bond, which is the wrong method. We always have to give consecutive number to the carbon double bond carbon. So this pink way of numbering is wrong, and hence we'll be following the yellow way of numbering, in which position 1 is to one carbon double bond, and the another second position is to another carbon double bond, and the third position is to the carbon where the CH3 is present. So the name will become 3-methyl cyclopropene. We are not mentioning the position of double bond because, as I mentioned, by default the position for double bond should be the position 1, and that's what we are giving in every case. Now, next, this compound, simple name, you have a double bond, 4-membered chain, cyclobutene. If you have 2 double bonds in the chain, in that case, what will you do? You will again start numbering in such a way that one pair of carbon double bond carbon should get position 1 and 2, and then accordingly respective positions have to be given to the another carbon double bond carbon. So I have given position 1 here, 2 here, 3 here and 4 here. So we have got 2 positions for double bond. One is 1 position, another is 3rd position. Okay, both the double bonds cannot get position 1 and 2. It has to be the continuous number. Okay, so I've got cyclobuta 1,3 diene. Cyclo to represent cyclic structure, buta to represent your chain is made up of 4 carbons. 1,3 is the position of the 2 double bonds, and diene represents that there are 2 double bonds present in the cyclic structure. Okay. By the way, let me just tell you one more thing about this particular compound. This particular compound is an unstable compound. Okay, and this compound is why it is unstable? Because it is an anti-aromatic compound. What exactly are anti-aromatic compound? We will be doing it going further. You just have to remember that this is an anti-aromatic compound. So basically we can have structures where you can have one or more than one double bonds, but mind one thing, so double bond can never be on the consecutive positions. That means if I would like to make this particular compound as this, double bond over here and double bond over here, this is not possible. Why? Because it is highly unstable compound. Why it is highly unstable? I'll tell you. See, if you look at the hybridization of the carbons, this carbon is sp2 hybridized, this carbon is sp3 hybridized, this carbon over here will become sp hybridized, and this carbon is sp2. Sp hybridized carbons I hope you know what is sp, what is sp2, what is sp3. So if you talk about sp hybridization is a linear hybridization. So if you talk about the shape of the compound which carries the sp hybridization, the shape should be linear. That means there should be angle of 180 degree, whereas the angle over here is around 90 degree, right? So that means it is supposed to have 180-degree angle, but it is getting 90-degree angle. So there is a lot of angle strain. The molecule will not exist, or you can say the carbon will not be able to form the sp hybridization due to the difference in the angle required to form sp hybridization, and what angle is exactly being formed over here. And this we and when you talk about sp is a planar geometry, whereas I mean planar linear geometry, whereas this is not linear, this is not the linear shape. So generally for the small cycles or small cyclic structures, we cannot have the carbons having sp hybridization in that. Reason being, again, we want a linear structure. Until unless the molecule can have that linear structure, can have that linear geometry and 180 degree or around 180 degree angle, the sp geometry is not possible. Okay, and if it is not possible, then the compound is also not possible. That is the reason why consecutive double bonds are not possible in case of cyclic structures. I must not say that these are not possible, but these are not possible till a certain number. So basically smaller cycles or smaller cyclic compounds cannot have consecutive double bonds, but if the chain grows to 8 carbons or more than 8 carbons, in those compounds there is a possibility of having the consecutive double bonds, because they can maintain the linearity, they can have that linear structure. But any cyclic chain having carbons lesser than 8 cannot have it, because they cannot maintain that linear shape or linear structure. They cannot, the carbon cannot have that linear shape or the angle which is required to be in sp hybridization, and hence the molecule will become highly unstable and it will not form. Okay, so consecutive double bonds are not possible in case wherever we have less than 8 carbons in the cyclic chain. So this structure is not possible altogether. If you have to have two double bonds, then it has to be on two different positions. Basically, these double bonds cannot be on the consecutive position. So this is the only possible way how you can have two double bonds in the cyclic butane, or you can in the cyclic four-membered ring. So you may find many a times this particular compound's name written as instead of cyclobuta 1,3 diene. In some books or in some questions, you may find just simply writing them as cyclobutadiene. So they won't mention the double bond over here, because there are only one fixed position where the double bond can be, that is alternate position, because the consecutive is not possible. Okay, and I have told you and explained you the same thing earlier, that wherever the position of something is going to be fixed, which cannot be changed, because the other way, there is no other way of forming the compound, then there is a possibility that you do not get positions in the question. Okay, so whenever they write cyclobutadiene, they are basically talking about this structure, because any other structure is not possible. Neither this is possible, nor this is possible, nor this is possible. So basically all these structures are same. So consecutive double bonds are not possible. So only possibility is this, and it can have name as cyclobutadiene without any position, or we can write the position and write it as cyclobuta 1,3 diene. As I mentioned, this compound itself is also unstable because of the special characteristic what it carries, and that is called as anti-aromaticity. What is anti-aromaticity? You will be learning when we'll talk about aromatic, non-aromatic and anti-aromatic compounds. That time we will again talk about this compound. So in fact, when you talk about cyclobutadiene, in any case, cyclobutadiene is not stable. Neither in the consecutive positions double bond is stable, nor on the alternate positions the compound is stable, but it can still exist. But this particular compound where you have consecutive double bonds cannot exist at all. Okay. So now let's talk about the next compound. This compound, you have 5-membered ring with one double bond, and this is called as cyclopentene. I don't think you should have any doubt over here. Now in this compound, again, we have double bonds. 2 double bonds are there. So I can start numbering from here. I can start numbering from here. 1, 2, 3, and 4. If I'll do the numbering this way, my double bond will get position 1 and position 3, and the name of the compound will be cyclopenta 1,3 diene. Now, can we shift this double bond and can we put it here like on the consecutive carbon? Here like this? No, we cannot. This structure is not possible. As I mentioned just now, that any chain which is lesser than 8 members or lesser than 8 carbons, there the consecutive double bonds are not possible, because the carbon which will have consecutive double bond, that will have the hybridization of sp, and your smaller cyclic chains cannot support the sp hybridization because they cannot maintain the linear shape or 180-degree angle which is required to make this sp hybridization, or which is required to maintain that sp hybridization. Okay, so let's talk about next set of questions. This compound, six-membered ring with one double bond, the name will be cyclohexene. I don't think you should have any doubt over here. In the next compound, I have a six-membered ring with a double bond and one CH3 as an open chain over here. Now it is very clear that my cyclic chain is bigger because it is six-membered. Secondly, it has a double bond, so automatically my cyclic ring is going to be the principal chain and the CH3 is going to be branch. And as I mentioned that we will give the position to our double bonds as position 1 and 2. So I'll mark the position as 1 and 2 over here. My CH3 got position 1 and hence the name is 1-methyl cyclohexene. Next, look at this compound. What I have here is I have a six-membered ring with a double bond and the bromine and chlorine attached to it. Right now, six-membered ring with a double bond. Obviously, this is going to be my principal chain. There is only one chain, by the way. There is no other open chain structure or anything like that. So the name of the main chain is going to be cyclohexene. Now we know that we have to give the position to our double bond as position 1 and 2. So how will we number? What we have to think while we are numbering? So we have to ensure that our double bond must get the continuous number. You cannot do in such a way that you give position 1 to one carbon double bond carbon and then you roam around in the whole molecule and then come back and then give the last number to the another carbon double bond carbon. So your carbon should have the consecutive numbers. Okay, secondly, now here I have to, so I have multiple choices over here. Ideally I can start numbering from here as 1 2 3 4 5 and 6. If I do the numbering this way, then what will happen is my chlorine will get position 3 and my bromine will get position 6. Okay, and my double bond is getting position 1. But you have to remember one thing what we have discussed in the previous part of this video. I told you that when it comes to name the halogens, you always go for the alphabetical order, or when it comes to number the branches, you have to see which comes first in the alphabetical order and you try to give it the lowest possible position. So if I number this way, my chloro is getting, which is alphabetically later, and bromo is alphabetically first. My chloro is getting a lower position, whereas bromo is getting a higher position. So we have to figure out, is there any other way of numbering? Let's try out. So I think there is. If I start numbering from this carbon, this will be 1 2 3 4 5 and 6. So blue way of numbering. My carbon double bond carbon is getting position 1. Along with that, my bromo is getting position 3, which is lesser than position 6. Right? And that is what exactly we want. We want the alphabetically first, whichever substituent comes, we have to try giving it the lower position. So we got the position 3 for bromo by this way and 6 for chloro. And this is what we will be following. We will not be following the yellow way of numbering. So the name of the compound is going to be 3 bromo 6 chloro cyclohexene. Now, come to the next example. In next example, we have two type of substituent groups. One is CH3 on the cyclic chain and other is two-membered substitution. So basically CH2, CH3. Okay. And I have a six-membered ring with a double bond. So wherever the double bond is, that is going to be my main chain. So the main chain name is going to be cyclohexene. You write hexanine or you don't write hexanine, just simply write hexene. It's not going to make any difference. Now we have to see how to number this chain. So while we are numbering, as I mentioned, whichever comes alphabetically first, that for that particular substituent, we have to try giving it the lower number. Along with carbon double bond, carbon should get the position 1. So if I number from here, position 1, 2 and 3, 4, 5 and 6. So in this case, see, this branch is ethyl, whereas this branch is methyl. So alphabetically ethyl comes first, and ethyl is getting position 3, which is relatively lower, and my double bond is getting position 1. So 3 ethyl, 6 methyl, cyclohexane. There could be another way also, but that would violate the rule. If I start numbering from here, 1, 2, 3, 4, 5, 6, in this case, my methyl will get position 3, whereas ethyl will get position 6, and this is not the right rule, and we have to try giving the lower position to the alphabetically first substituent along with carbon double bond carbon as position 1 and 2. So we will be following blue way of numbering, and the name will be 3-ethyl 6-methyl cyclohexane. Now, let's talk about the next question. I'm feeling that I'm going a little faster, but I'm hoping that you guys are able to understand because we have done a lot of questions before. If just in case you are stuck somewhere, you're not able to understand, you can ask me in the doubt session. You can stop the video, think over a question, and mark the doubt whatever you have in a particular example or a question. So now in next example, we have a 6-membered ring with a double bond. So this is going to be a main chain, and then we have 2 branches over here. Both the branches are CH3 and CH3, right? So now I can mark my one carbon as carbon 1, another carbon as carbon 2, both the carbons carrying double bond, and there are 2 methyl groups which are present on those carbons itself. So the name will be to 1, 2 dimethyl cyclohexene, cyclohexanine, or cyclohexene. You can write anything. Now come to the question number 14. In question number 14, so basically this is the variation where I have taken a cyclohexene and then I'm placing methyl groups on the different positions, and we are seeing how it will differ the name. So here I have again 2 branches. One is CH3 here, another is CH3 here, and what we are doing is, again, my cyclohexene is going to be the main chain. Here we are basically trying to understand the way of numbering, how it changes if the position of the branches change. So if I number from here, I'll get position 1, 2, and 3. So my one methyl will get position 1, another methyl will get position 3, and the name will be 1, 3 dimethyl cyclohexene. So now let's talk about question number 15. In question number 15, again, cyclohexene is my main chain, and I have 2 branches, again CH3s, but on the different position than the previous cases. So now here what we'll do, again, when we'll start numbering, we will number it in such a way so that my carbon double bond carbon should get position 1 and 2, but along with that we will try to give the lower positions to the branches also. So I will start numbering from here: 1, 2, 3, and 4. Why from here? Why not any other way? Let's try out the other ways also. So this is the thing, and I have a CH3 here and I have a CH3 here. I could have started numbering from here: 1, 2, 3, 4, 5. In that case, my one methyl would have got position 2 and another methyl would have got position 5. Totally not recommended. Other possibility is I could have taken this is as position 1, 2, 3, and 4. 5 and 6. So this is a very wrong way of numbering because our carbon double bond carbon should get position 1 and 2, and moreover there is no added advantage by using this way of numbering because eventually my CH3 is getting position 1 and 4 only. Even though if there would have been an advantage of the let's say position, you would have got a better position, but still we will not use this way of numbering because we want a consecutive number on carbon double bond carbon. So this is also not done. So this is the only way how we are going to number our chain. So the name of the compound is 1, 4 dimethyl cyclohexene. Now let's talk about the next compound. Here is the compound. I have 2 CH3 groups again. Cyclohexene is again my primary chain or principal chain. Again, as I mentioned, we will be numbering the consecutive numbers and we will try to give the branch as the lower position as possible. So I'll start numbering from here: 1, 2, 3, 4, and 5. So I have 2 methyl groups. One will be on position 1, another will be on position 5, dimethyl cyclohexene. Can I use any other way of numbering? Let's try out. So I could have started from, let's say here, 1, 2, 3, 4. So in this case, see, if you see, my carbon double bond carbon is getting again 1 and 2 position, but my one of the methyl is getting position 2 and another methyl is getting position 4. If you look at the previous case, what I have chosen, position 1 and 5 is the thing. So sum is not different, by the way. But here, the first substituent what we are encountering, we try to give it the lowest possible position. Lowest possible. So though I can give it second position and 4 to the other substituent, but if I do it other way, what will happen? At least my one substituent will get the lowest possible position, and lowest possible position is position 1. So if I have a choice where the sum is coming same, I will try to give the lowest possible number to my first substituent what I am encountering. Okay, so here my this CH3 could have got position 2 and can get position 1 also, but I will try to give it position 1 if it is possible in any way. Okay, so this is position 1. The other substituent will get its position automatically, but the first substituent should get, or the first encountered substituent should get the lowest number possible. Okay, so here I have got position 1 and position 5, and the name has become 1,5 dimethyl cyclohexene. So you can make a small note over here, the rule which I have mentioned. You can just write it as try to give the lowest number or position to the first locant. So here what I'm trying to tell you is lowest sum rule will not be preferred. We will prefer the lowest locant rule. That means my first locant or first substituent should get the lowest position, even though the sum is coming a little greater, but still we will follow the lowest locant rule over lowest sum rule. So here I'll just mention it once more. Lowest locant rule is preferred over lowest sum rule. Now let me tell you what is lowest locant rule. Lowest locant rule means the first locant. Locant is nothing else but substituent or the side chain or the branch. It's just a fancy name for it. So any side chain, the first side chain which you are encountering should get the lowest possible position, and the other will automatically get the respective position. You will not prefer the numbering in such a way that your lowest locant rule is getting violated. So let me just give you an example. So now let me take an example. So if I take this as a question, in this case, I have again two CH3s present on different positions and a double bond over here. So I have two ways of numbering. I can number 1 here, 2 here, 3, 4, 5 and 6. In this way, my one methyl will get position 1, whereas the another methyl will get position 6. Right? If I do not follow this way of numbering and instead I start numbering from here, my positions will be 1, 2 and 3. So I will get position 2 and 3 for my methyl groups, which is basically the lower sum. But I will not prefer it. We will prefer this. Why? Because the first locant, or you can say first substituent which is encountering, we will try to give it the lowest possible position, and lowest possible position what we can give to our locant is the 1 position, because we can start numbering from here and then we can go the other way around by giving it the position 1. So we will not follow the lowest sum rule over here. Instead we will be following the lowest locant rule. That means the first substituent what we are going to encounter, we will try to give it the lowest possible position. Okay, so this is something which is a little tricky, but yeah, that's how we number it. So the name of the compound will be 1,6 dimethyl cyclohexene. That's how the name would be. Okay, so here we are done with most of the cases what we can have for this cyclohexene with the positions of methyl groups on the different position. Let's see a few more examples now. Okay, so now next set of examples. Oh my God, by the way, I have already written this example which I was explaining you before. So the name, as I have mentioned, we will start numbering from here 1, 2, 3, 4, 5 and 6. Why we have preferred this way of numbering, though the sum of the positions is more, because we are following the lowest locant rule. We ignore the lowest sum rule. So we do not look out for the positions of the branches, the sum of position of the branches is lowest or not. We actually look for that the first locant what we are encountering is getting the lowest possible number or not. And by writing 1 over here, we are getting the lowest number possible for my locant, and hence the name will be 1,6 dimethyl cyclohexene. Now let's talk about the next compound. Okay, basically you try these compounds on your own and then I will discuss the names. There are 3 compounds written over here. Pause the video, try out these compounds, and then we will see what are the name of these compounds. Okay, so let's look at the question number 18. I have three branches over here. All the three are methyl groups on the different positions. We know that we have to number our carbon double bond carbon as 1 and 2. So I will start numbering from, let's say here. I will use the multiple methods too. 1, 2, 3, 4, and 5. This is one way of numbering. Another way of numbering, let me just write it over here. So other way of numbering can be starting from here 1, 2, 3, 4, 5 and 6. So by this way of numbering, I'm getting position for my branches as 3 comma 4 comma 5. By this way of numbering, I'm getting the position as 4 comma 5 comma 6. So this is definitely not preferred. This way of numbering will be preferred. So now we have got that our branches have position 3 comma 4 comma 5, whereas our double bond has position 1 and 2. So position 1 is something what we talk about, and this will be cyclohexene. So main chain is cyclohexene. Whereas I have three substituent groups, all the three are CH3s positioned on third, fourth, and fifth position. So I will write it as 3, 4, 5 trimethyl cyclohexene. Check out your answers, see if you have any doubt in this case. Now, if not, then let's move to the next example. In next example, what we have is two branches and one cyclohexene. So let's first write cyclohexene because we know at least this is going to remain same. Cyclohexene. Now we have to figure out the name of these branches which are present over here. So branches, as we can clearly see, these branches look like the complex branches which we have discussed earlier also in the alkanes topic. So if I try to resolve it, this will be like this: CH3 and CH3. This is one branch, and other branch is CH3, CH3, and CH3. So these are the branches. So none of the branches out of both are the normal branches, but these are the complex substituents where the branch is there within branch. So we have a different way of naming, which we have already discussed earlier. So here what we'll do is we'll try to find out the main chain of the branch itself. So here, so let's mark the main chain here of the branch. So this is two-membered carbon chain. I'm not very sure whether it is clearly visible to you guys or not. I have not written it very neat though. So this I have taken as the part of the main chain, and this will be acting as a branch of a branch. So this branch is made up of two carbons. So name is going to be ethyl. And as I told you earlier also, that when we are talking about the branches which have furthermore branches, then how do we number those branches? The carbon which is directly connected to the principal carbon chain or the parent chain will always be numbered 1. So this carbon is carbon 1 and this carbon is carbon 2. So I have a CH3 branch on a branch at position 1. So it will be 1-methyl ethyl. This is going to be the name of this branch. This branch. I hope you can recall what we have done in the alkanes part, and this is how exactly we name the complex chains or complex substituents. Now let's talk about the next branch what we have. This is also a complex substituent. So as I've told you, this is going to be the carbon 1, and I have to find out the longest continuous chain for the branch. So it will be this. You can actually take any one. I have taken this because it is going to give you the same length all over. This is my chain, and it has the branch further has two branches. Both the branches are present on the first carbon. So I will write the name as 1,1 dimethyl. Why dimethyl? Because two methyl branches are present on the branch, and branch itself is made up of two carbons, and the name of the branch is ethyl. So I have two names over here. One is 1-methyl ethyl and another is 1,1 dimethyl ethyl. So these are two branches which are present on the cyclohexene as the complex substituents, right? So now these branches will be named here when we'll write the name of the compound. So now we have to figure out how to number these branches or how to number the cyclohexene chain. So how will we number? Look at the names of the branches, and we will be numbering them according to the alphabetical preference. Okay, alphabetical preference. Both have methyl ethyl. Earlier, what we generally do is we ignore the di, tri, and tetra. But because here the only thing what can distinguish in the name is di and no di basically. So here alphabetically this D comes first because methyl ethyl part is anyways same. So this will get the higher preference alphabetically as compared to this, and we will try to give this the lower position possible along with carbon, double bond carbon as 1 and 2. So I will mark it as 1 here, 2 here, 3 here, 4, 5 and 6. So we got 2 positions, 3 for this and 6 for this. So how will we name this compound? Let me just write. So the name of the compound will be 3, let me just write it with a different color pen. So it will be 3-1, 1 dimethyl ethyl. This is my first branch. Then comes -6-1 methyl ethyl. And then comes cyclohexene. I don't have space, hence I'm writing it down, but you don't write it this way, okay? Because we don't leave gaps in the names. So 3-1, 1 dimethyl ethyl, 6-1 methyl ethyl cyclohexene. That's how the name of the compound would be. Here you have to notice one more thing, that this compound, this branch basically, this branch which is 1-1 dimethyl ethyl, we have already spoken about this branch earlier in some common names, or you can say I told you what is tert butyl, and when I told you what is isopropyl. At that time we have discussed these branches, and this particular branch which is 1-1 dimethyl ethyl has another name, and that is tert butyl. We can also write it as tert butyl, and 1-methyl ethyl can also be named as isopropyl. Okay. So isopropyl and tert butyl, both of these are the names for these compounds which are acceptable in IUPAC naming. And you may find questions where they have used isopropyl and tert butyl in the name rather than using the actual IUPAC name, the way how we have named the complex substituent chains. So we can also write the whole compound's name as 3-tert butyl. Why tert butyl as on the third position here? Because tert is something what we are ignoring. We are considering B of butyl for the alphabetical order, and then comes my isopropyl. I am ignoring iso in the alphabetical order, and I am considering P as the alphabetically order, as in the alphabetical order, and hence P comes later than B. Automatically butyl will get preference, and this will become cyclohexane. That's how you can name. So you can name it this way or you can name it this way. Both the names are right. Okay. Now come to the last question. So in the last question, what we have is double bond now is not on the cyclic chain. Instead, it is on the open chain. So this is going to be the main chain and the cyclic structure is going to be as a branch. So how will we name it? This compound, this open chain is made up of 2 carbons. So it will be ethene, right? Let's mark it position 1 and 2. Put on the position 1, we have cyclohexyl present. So the name will be cyclohexyl ethene or 1-cyclohexyl ethene. You can name it either way, right? I hope you have understood. So basically there was an important question, that was 19th question. It was a little important in terms of multiple applications of multiple concepts what we have learned. One is complex substituent naming, and another is using the common name as isopropyl and tert butyl and all that. So this is a very important example. Let's talk about the next few examples. So these are some last set of questions which you try out on your own, and then I'll discuss the answers and I'll discuss the name of these compounds. We'll tell you how exactly we are going to name these compounds. Okay, so now let's quickly discuss the name of these compounds. Let's look at the first compound what we have. The first compound what we have has the double bond present in the cyclic chain as well as the double bond present in the side chain. Now when both have the double bond, we have to look out for the length. So length is greater for the cyclic chain. Automatically my cyclic chain will be acting as the principal chain and my side chain will be the open chain. So this is my principal carbon chain. So the name of the principal carbon chain is cyclopentene. Right? Now we have to figure out how to name the branch which is an open chain. So open chain branch is a alkene. That means a double bonded structure. And we have already studied this, that when an alkene acts as a branch. These are called as alkenyl groups, okay? And the alkenyl groups have the suffix enyl. So I will count the total number of carbons here, 1 carbon and 2 carbon. The compound will be called as ethenyl. So this will be 1 ethenyl cyclopentene. Why 1? Because we always give position 1 and 2 to the carbon double bond carbon. So on the first position, you have this branch present, which is ethenyl. I hope you would have understood, because we have done this ethenyl thing earlier also, and we have seen many examples of this kind. Now look at the next compound. In next compound, we have again the similar kind of compound where the cyclic chain as well as the open chain both have double bonds, but my open chain has 2 double bonds, basically more unsaturation than your cyclic chain. And we have talked about this rule that wherever the number of double bonds are more, that will act as a main chain. So automatically, my open chain becomes the main chain, and the cyclic chain will become what? The cyclic chain will become a branch. So this cyclic chain is a branch, and the main chain is the open chain. How many carbons are there? Carbon 1, carbon 2, carbon 3, carbon 4. So 4 carbons are there in my open chain with 2 double bonds. How will we position it? We will start positioning from here, 1, 2, 3 and 4. So my double bonds have 2 positions, 1 and 3. So the main chain name is going to be buta 1, 3 diene. I hope you have got it. So there are 2 positions, position 1 and position 3 for the double bonds. Now let's see how to name the cyclic structure. So this cyclic structure is actually cycloalkene, but when it is acting as a branch, it will automatically will become cycloalkenyl. Right? What is cycloalkenyl? When from cycloalkene you remove one hydrogen and that particular thing starts acting as a branch, then it is called as cycloalkenyl, and this will become cyclopentenyl. Where it is present exactly, it is present on the first position of the principal carbon chain, and hence the name will be 1-cyclopentenyl buta 1, 3 diene. Okay, understand it very carefully. It is very important. Now again, let's talk about the next example. In next example, we are just adding things so that we can make sure that we have understood all the rules properly. Now in this, the number of unsaturations are same. So what is going to be different? The chain length is different. So my cyclic chain is bigger in length and the side chain is smaller in length. Side chain has 4 carbons, whereas the cyclic chain has 5 carbons. Hence my cyclic chain will act as a parent chain or principal carbon chain. So I'll start numbering from here, 1, 2, 3 and 4. So I've got 2 positions for my double bonds. One is 1, another is 3. So name of my principal carbon chain is going to be cyclopent 1, 3 diene. Right? Now what is the name? What is the name of this open chain is where the 2 double bonds are? The same way how alkenyl groups are there, exactly same way when you have 2 double bonds, it will be just alk dienyl group. There is no difference. It's just a bit of common sense that it's the same when you have alkene with 2 double bonds, or basically a chain with the 2 double bonds, you call it as alk diene. Right? So when you remove one hydrogen from here and that particular thing start acting as a branch, it will be dienyl. That's all. Just simple. Instead of enyl, we'll be using suffix dienyl because it will represent that we have 2 double bonds in the carbon chain. So here we have the 4 carbons here, 1, 2, 3 and 4. If we mark the position of these double bonds, position is 1, 2, 3 and 4. So 2 positions, one is position 1, another is position 3. So my double bonds in branch are on 2 positions. One is at 1 position, other is at 3rd position. We have to give the positions to these double bonds also, even in the branch. And I told you the branch which is attached to the principal carbon chain, from whichever carbon it is attached, that carbon will always get position 1. Hence I have given it position 1. So the name of this branch is going to be buta, and the position of the double bonds is 1, 3, and di N, it's not completely ene, it's enyl. It's a branch, hence we will write it as enyl. And the position of this branch itself is position 1. If you see over here, this is position 1 of the cyclic chain, and hence we will write it in the round brackets. These kind of branches comes under the complex branches, and these are generally bracketed so that you don't get confused, and it will be easier for you to identify the difference between the branch within branch position or the double bond within branch position and the branch position on the principal carbon chain. So this 1 is the position of the branch on the principal carbon chain, whereas this 1 and 3 is the position of double bond in the branch. Okay, so we put the round bracket to make it a little more clear and easier to understand, and it is important, do not miss writing that. All the complex substituents must be in the brackets. Now the last example we have, I have taken triple bond over here. So basically I'm not doing cycloalkynes separately. All the rules of cycloalkenes are equally applicable in cycloalkynes, and the behavior and the way of naming, numbering, everything is exactly same. Only difference is instead of "-ene" we'll be using "-ine". So I've just taken one example so that you can see how we name it, how cycloalkynes are named and how the name looks like. Rest of all the rules are same as alkenes. So I have a triple bond over here. I have a branch over here. I know there was no branch when you noted down the question. I have made this branch just now. Okay, so 1, 2, 3, and 4. I just added a branch to add the complexity. That's all. So my double bond has the position. Sorry, my triple bond has the position 1, so it will be, how many carbons are there in this chain? 8 carbons are there, so it will be oct-1-ine, and I have a methyl group which is present on the 4th position, hence the compound name will be 4-methyl cyclooct-1-ine. So here we are done with the cyclic alkenes or cycloalkenes. Next, we will be talking about furthermore additions in the cyclic structures or some more complex chains in the cyclic structures, and we will be done with the cyclic compounds by next class or next video, and then we will start the functional groups. Okay, so here we are 80% done with the cyclic structures. So there are still few compounds which are left. There are still few types which are left, which we will be covering in the next class.